So we'll have a little bit of hand waving there, lots of hand waving, but in the end you get strong empty completeness of edge unfolding polyhedra. Any questions? All right, perfectly clear then. Let's move to another puzzle. This is called the snake cube puzzle or the Kubra puzzle. Here is one instantiation of it. So we have, it's a chain of blocks. Try to unfold in a way that I can put it back together because it's actually quite tricky to solve. It's a chain of blocks and there's an elastic through the centers, going through the center of the faces. And so the result is, you can't really pull the squares apart. It's a pretty tight elastic. But you can spin, because from the elastic's point of view, these are all equally happy. So you're basically told that, I could also spin here, but it doesn't do anything. That stops at a 90-degree angle. So I'm forced to be straight here, and then I'm forced to have a 90-degree turn. And then I'm forced to go straight, and then have a 90-degree turn, and then go straight, and then have a 90-degree turn. Here I have a few 90-degree turns in a row, and that's the general structure. And can I still solve it? Maybe. The goal is to get into a cube. Okay, and there are a bunch of different versions, plastic, wood, whatever. This one is not solved, and so I will not do so well, but you get an idea of what it looks like in its sort of flat state. I'm going to make it into a staircase. So in general, this puzzle is specified by a sequence of lengths, of straights, and then in between those lengths are the 90 degrees. Okay, so that's the puzzle. Pretty simple specification. And your goal is to fold into the cube. You know how big the cube is. You just take the number of little cubes and then take the cube root. This puzzle maybe goes is at least 1990, but could be later. Exactly. And this puzzle is also incomplete. And this proof is also complicated. So we won't see all the details, but this one we'll probably see a little bit clearer. This is a proof by, in particular, the three of us, and Marty and Bex, all four of us. And let's see. So this doesn't look like a cube. So before we try to solve the problem of folding into a cube shape, let's suppose I give you one of these chains and I want to know, can it fold into this shape? Let's say this is the target. So it's a big box down here, called a hub, and then there are these spokes, or just big boxes, long boxes, sticking out of the hub. There's a hole here. They're connected to the main structure. You want to fold that. And let's see. So the big idea, we're reducing from three partition here. We're going to represent a number AI as a zigzag. Well, I'm sorry, I shouldn't call it a zigzag. But we have a really long bar, then a length 1 bar, and then a really long bar and a length 1 bar. I'm drawing sort of the thinned version. This is really a little cube. This is a little cube. These are lots of cubes. Huge number of cubes. Okay, so that's really, really big. So big that the only place it could fit is down one of these spokes. So of course the idea is that these represent our triples, whose sum is equal to t. And so we have to take these things, and because these are so short, you can't like go out of one hub and like jump to the next one, because there's a gap there that's bigger than 1. So once you commit to having one of these long bars into one of these pockets, then all of them have to go into the pocket. So this is, in general, a big issue with three-partition proofs, is you want to represent the number AI in some way that cannot be, is not divisible. If you could take AI and split it into two parts, then the packing problem becomes trivial. Split everything into units or something. So we have to make sure AI remains a single chunk. We are, of course, encoding AI in unary here, so we have one long bar per each AI, but for three-partition, unary is okay. There's some things going on here a little bit weird. So you see this thing is occupying the full length, and the length here is going to be 8 times the target sum instead of just the target sum, and we're multiplying this by 8. So those are equal, we're fine. There's a reason for the 8, which we will get to. Okay, now, like the previous proof, the edge-unfolding polyhedra, we have these great units, and we just like them to be free-floating. And if you generalize this puzzle a little bit and say, well, actually, I don't just have one chain, I have two chains, or I have n chains, and together, collectively, they have to fold into this shape, then we're done, except we remove the box, the box over here. Because then these guys just somehow have to be assigned little pockets, and we're happy. Okay. All of these numbers, although, again, not drawn to scale, all of these numbers are much smaller than huge. So you can't, like, take this guy and put it here, even though in this picture it looks like you might be able to. All right. So the issue is now we want to connect this together into one big chain. We have these units for each eye. We have one of these units. That's cool. And we want to attach them together in a way that is super flexible, just like the atoms we had before. Now we're going to use something which we call zigzag, so I didn't want to call this a zigzag. This is all unit segments. So you have 90-degree turn, 90-degree turn, 90-degree turn, 90-degree turn, no straights. This turns out to be universal in a strong sense. It can fold into anything. And so we can use it to connect these parts together. So what we're going to do is have the A1 gadget. Then we're going to have a whole bunch of zigzags so you can go wherever you need to go. Then we'll have the A2 gadget, and then we'll have the universal zigzag gadget for a long length of it, and then the A3, and then alternating between zigzags and the AI. And at the end, we'll have enough zigzags that we can fill all this sort of extra garbage space. But we will use this garbage space in order to route around. So maybe A1's going to go here, and so we do this thing. Yeah, looks like some kind of cooker. We go back and forth like that. Then we'll have the zigzag and say, okay, I want to go over here next, and then we'll do A2 there, and then we'll route over here. And because this is in 3D, crossings are not an issue. I could just go out into the third dimension. We don't need much of a third dimension. 8 is enough. You can just, enough to go over each other. Okay, and then at the end, we're going to fill in all the space with the zigzag. So let's talk about the zigzag. What we claim is a couple of different senses in which it's universal, but the key idea is sets of gadgets. So we're drawing here a 2x2x2 cube made up out of 8 little cubes. And if you look at what we've drawn here is the elastic that goes through the centers of the cubes, and notice it turns 90 degrees at every voxel, at every little cube. So this is part of, these are zigzag constructions. So what we want to say is that if you sort of, one sense of universality is that the zigzag structure can fold into any polycube structure. Polycube is the 3D generalization of polyominoes that we saw last time from polyomino packing. That's not true. But if you take any polycube structure and you just scale it by a factor of 2, so you replace every cube with a 2x2x2 grid, like this picture, then it's still not true, but it's better. So what's true at that point is if you take any half of 2x2x2 cubes, this is what